Are you struggling with IFC models that fail to meet strict BIM requirements? You are not alone. This is a topic that's becoming increasingly important. However, ensuring accuracy and compliance can be a real challenge. In this video, we will provide a clear step-by-step guide on how to prepare and export IFC models using Tekla Structures, tailored to meet demanding BIM standards. And maybe you want to make changes after exporting the IFC file. We will show you IFC Post Processor, which allows users to add, modify, or delete entire tabs or individual attributes directly within the IFC file. In other words, we will learn how to streamline your workflow, avoid common pitfalls, and confidently deliver models that meet your client's expectations. We will cover the entire process with practical examples. We will start with introduction to BIM requirements and the responsibilities involved. Next, we will discuss the initial condition, what you need to know at the beginning, including the impact of various factors on the entire process. Finally, the main chapter will focus on model preparation. I will show you how to prepare a model directly in Tekla, covering tasks like dividing the model into floors, adding extra information, exporting the IFC itself, and then handling the IFC on selected examples. Of course, requirements may vary depending on the project and the organization providing them. So why do we need BIM requirements? The quality of BIM models is crucial because we want to integrate all models with information from other sources, ensuring we can trust the data is accurate and correctly placed across all projects. Requirements dictate how BIM model must be created, what information they should contain, and how that information is structured. Different elements at different stages of the project require different information. Individual specialists, architects, structural engineers, or other professionals are responsible for providing this data in their models. Here we can see workflows showing the different stages of the process. Each stage may have different requirements for software or even software version. We will use the Statsbygg SIMBA BIM requirements as an example, but remember that the requirements may vary depending on the project or client. For instance, individual companies or institutions like Veidekke may have their own set of requirements. The design tool, the software, plays a significant role in this process. The functionality of the software, including differences between versions due to updates, can either simplify or complicate the process. In this presentation, we will use Tekla Structures 2023. Another important factor is the version of IFC 2.3 or 4.0. These formats are evolving and the information they can handle may differ. We will be working with IFC 4.0 in our examples. Finally, a BIM checker. This tool is also crucial. While there are many software options for IFC visualization, each may display data differently. For this presentation, I will use Solibri to demonstrate how to resolve some common incompatibilities. Now, onto the main topic, model preparation. I've divided this into two chapters. First, pre-process, preparing the Tekla model, and this involves creating a spatial hierarchy by dividing the model into building and floors, adding additional information to elements, setting the correct EFC entity types for Tekla elements, exporting the EFC model with the required information. And second, the post-process, preparing the IFC model using the IFC Post Processor application. This will allow us to add any information that might be missing directly in IFC. Let's start by creating a hierarchy structure in our model. Currently, Tekla offers two methods to do this, and I will show you both. Here's an example of the desired outcome. We have IFC in Solibri divided into floors, which can be easily selected. To do it, we will open Organizer. On the right side, under Categories, we need to find Building, right-click and open Define Boundary Box for Location. First, in Building tab, we define the range of our building. We can visualize this by clicking the cubic icon on the left side. We can drop Section tab. The floor system we can create automatically based on the grid system along the Z-axis. So it's important to prepare it correctly in advance. At the end, click Modify to upload changes. You can also visualize particular floors by clicking the cubic icon on the left side. Now we can see that all elements are divided and added to created floors. We can highlight them by clicking Select in the model. Empty, uncategorized group means that we don't have any ungrouped elements. Such prepared model we can export to IFC. Crucial is to have selected option Spatial Hierarchy from Organizer to include our hierarchy structure. We can see that now our model is divided into floors. The second and newer method is using building hierarchies function. As default, it's grayed out, so in order to activate it, we need to go into advanced options and change building hierarchies from false to true. We need to also reopen Tekla. Now building hierarchy is available. To easily add floors, I will use section view. By clicking the level button and choosing single Z-axis, I will add floors to our spatial hierarchy. We can change names and range manually. To display or hide floors in particular view, use display settings. Now in Organizer, after synchronizing, we will see that all our elements are grouped into floors. Such prepared model we can export the same way as before. After setting up the hierarchical structure in our model, the next step is to create the required additional data for our elements, commonly known as user-defined attributes, or UDAs. UDAs allow us to include custom information in our model, which is essential for meeting specific project requirements. For this demonstration, we will focus on adding Statsbygg TFM properties required at level 2 of the project, but keep in mind that this approach can be adapted to any additional information. In this example, you can see additional tab NONS reference from Statsbygg requirement. To fulfill and export these attributes, first, they need to be created in Tekla. This process involves setting up a new tab with the necessary attributes. Tekla provides a set of standard tabs and attributes for each element type. However, we often need to add our own attributes, either for internal use or to meet external project requirements, as in this example. To create a new tab with custom attributes, you can modify the existing object's ENP file or create a new one. This new file will merge with the existing attributes the next time the Tekla is open. In our case, I will create a new object TFM ENP file in the model folder and define the necessary attributes. For detailed guidance on how to create and integrate these attributes, the Tekla support website offers step-by-step instruction. I would like to add here that it's important to distinguish between the UDA's label, what you will see in Tekla, and UDA's name, what appears under IFC export, as this is crucial for include correct data. Finally, we must assign the new tab to specific Tekla object types to ensure it displays correctly. This step allows us to control which Tekla object type will have the new attributes. After completing these steps and restarting Tekla, the new tab will be available in the model, ready for input and export. Now let's focus on ensuring that elements in Tekla model are grouped and assigned to the right IFC entity types. Here we see an example where elements are grouped under different IFC types. Notice that this object is exported as an assembly with the IFC BIM entity and consists of parts exported as IFC BIM and IFC plates. To achieve IFC models with properly categorized elements, what is usually required, we need to set the IFC entity type in Tekla before export. These types located on the side panel under Element Properties are essential for defining how our Tekla elements will be classified in the IFC model. It's important to distinguish between Tekla object types and IFC entity types. They don't always correspond directly. For example, a Tekla steel beam should end up in IFC as a beam, while a Tekla concrete panel should be categorized as a wall in IFC. Additionally, you need to differentiate IFC entities for parts and assemblies. When elements are created in Tekla, parts usually gets the correct IFC entity type automatically. However, assemblies, as default, get IFC element assembly, which might be too broad for specific client requirements. In these cases, you should manually adjust the IFC entity to more descriptive type. Ensuring the correct assignment of IFC entities is crucial for creating a well-structured, compliant IFC model that meets project requirements. Now, with our model divided into floors, the required attributes added, and the correct IFC entity types assigned, we can proceed to export the model into IFC format. Tekla offers two versions of IFC for export, 2.3 and 4.0. In this example, we will use the newer IFC 4.0 format. The export window provides several important options. Let us briefly look at the export types. Reference view, used for reference files, exporting recesses as separate objects. Design transfer view, intended for additional editing. This is the option we will use. Bridge view, designed for bridges based on the IFC 4.3 schema. An EFC 4 precast view supports the fabrication data transfer workflow. We'll explore additional property sets in more detail shortly. We will utilize the spatial hierarchy we've already established in the organizer. In object types, we will export elements as assemblies, excluding grids and reinforcement to maintain focus on the essential elements. Now let's come back to the additional property sets. Here we decide which IFC object will inherit selected data from Tekla. This step is crucial for ensuring that previously added UDAs will be correctly exported and exist in IFC. For our example, we will focus on walls and hollow cores, which correspond to the IFC wall and IFC slab entity type. First, we will give our property set a name to be able to upload it anytime later. Next, we are creating a new tab which will display in IFC. Here we have different groups of IFC entities. Structural are the one we will focus on. On the left side, we're selecting which IFC entity types will get our new tab. Then, which attribute or UDA we want to include in our tab. Thanks to created previously INP file, we can find our UDAs here. And here we can see UDAs names, not labels. We can decide and change the name of UDAs that appears in EFC. Remember to save before closing, and such prepared model we can export to IFC. We can see that both the walls and hollow cores have a new tab NONS reference with all selected UDAs. Let's assume we've already exported our IFC model, divided into building and floors with elements sorted by IFC types and all required attributes assigned. While the IFC looks good, there may still be additional requirements that are challenging or even impossible to set directly in Tekla. To help users meet these requirements, we have developed the IFC Post Processor application at BuildingPoint Scandinavia. This tool works directly on the IFC file, but has access to the Tekla model and all its information. It allows users to add, modify, or delete entire tabs or individual attributes within the IFC file. The IFC Post Processor is available on Tekla Warehouse and is free for all BuildingPoint Scandinavia customers. I will demonstrate 3 common cases where this tool can be particularly useful. In the Statsbygg template document SIMBA 2.1 for structural engineering, there is a requirement for long name information on all spatial hierarchy levels: project, site, building, and building floor. There is also a demand for description of each IFC type, such as slabs and walls. Lastly, there is a need to specify whether an element is external and load-bearing. While this information appears correctly at the part level, it is often incorrect at the assembly level. If we check our IFC file, we will find that the long names are missing at the spatial hierarchy levels. Similarly, we are also missing description for walls and slabs. Additionally, the is external and load-bearing information may need correction at the assembly level. Currently, these issues cannot be fixed directly in Tekla. Therefore, we will use the IFC Post Processor to open our IFC file and make the necessary adjustments. After downloading IFC Post Processor, we will find it under Application and Component tab. First, we are uploading IFC we will work on. Then, to fix first example, choose IFC Entity Hierarchy and Building Level to add required long names. To map the building in the IFC to the corresponding building in Tekla, we need to use the same building name as it is in Tekla. We will check the name in the organizer. Then, we're adding long name, and that's it. To map the right floor for EFC building store, instead of names, we need to use bottom elevation. Then add proper long name, and at the end, click Post Process button up at the bottom. We can see that now both building and selected building floors have filled the long names. Next case, how to add description. We are selecting IFC entity we want to work with, and we're adding description. What is great is that we can use existing in Tekla attributes or properties. Here, each element will get as a description its name and profile. Now we can see that description is filled as expected. The last example, how to fix is external and load-bearing attributes on assembly level. Choose IFC Entity Assembly, then object type you want to work on, and under Property Set find interesting you attribute. In this case, is external and load-bearing. Here we will take correct value from part and assign it to our assembly. We can see that values are now correct on both part and assembly level. And that brings us to the end of this presentation. I hope this information has been helpful in clarifying the IFC export process. Thank you for your time.